Now it's time to learn about Newton's law of universal gravitation. This is the complete law of gravity that is more general than just W equals mg, like we've learned about so far. This applies to all sorts of objects in all sorts of different circumstances, not just objects near the surface of the Earth. So Newton, well, in my opinion, he was the greatest scientist who ever lived, and he figured out all sorts of stuff about physics. We've already learned his 3 laws of motion. Now, Newton realized that there must be some centripetal force holding the moon in its orbit around the Earth. Otherwise, the moon would just continue in a straight line because of Newton's first law of motion. So Newton deduced from his own first law that there must be some force directed toward the center of the moon's orbit to keep it from flying off into outer space at constant velocity. Just like the merry-go-round example we talked about in the previous video. Now, Newton's stroke of genius was realizing that the force that holds the moon in orbit around the Earth is the exact same force that governs gravity for objects in our everyday life. So Newton realized that the same force that makes this pen fall to the ground is the force that holds the moon in orbit. It's the force that governs the orbits of the planets around the sun. So that's why this is known as universal gravitation, because it applies universally to all objects. Now, there's a formula for the magnitude of the gravitational force. This is the more general formula, not just F equals mg. This applies to all sorts of situations. So it looks like this. The gravity force, I'm not using W anymore. I'm going to use F subscript g, meaning force of gravity, equals capital G, this is a constant number that I'll show you in just a second, times the mass of object 1 times the mass of object 2 divided by the distance between objects 1 and 2 squared. Okay, so this number, capital G, is known as the universal gravitation constant and has a value of 6.67 or 6.673 times 10 to the minus 11 newtons times meters squared divided by kilograms squared. So let's think about what this means. Let's interpret this equation. Let's say we have 2 objects. Object 1 has mass m1. Object 2 has mass m2. And we can draw a line between the centers of those 2 objects, and we'll say that distance between the 2 centers is r12. So now, there's a gravitational force. This is a field force. These objects aren't in direct contact, but they're still pulling on one another. And that field force has a magnitude equal to this constant number times the product of the 2 masses divided by this distance between the 2 objects squared. So we can see that the gravity force gets stronger with larger values of the masses, and it gets weaker when the distance gets greater. The farther apart the objects are, the weaker the gravity force is. And in fact, it depends on the inverse square of the distance, 1 over the distance squared. This is known as an inverse square law. Whenever there's a force that depends on the inverse square of the two objects, those forces share some common properties. So the most common forces that we'll encounter that obey the inverse square law are the gravity force and the electric force that you'll learn about in Physics 7. And it turns out that whenever objects follow this inverse square law, then you can treat each object as just being a point, essentially. The gravity force that's generated by a sphere is the same as the gravity force generated by just a small point where all the mass is concentrated. And this phenomenon is known as Gauss's law, after the famous mathematician Gauss. If you take Calc 3, you'll learn where Gauss's law comes from. So this is the magnitude of the gravitational force. Let's think about the direction of it. It's directed along the line that connects those two objects. And gravity is always attractive. Objects never repel one another with gravity. They always attract. So the gravity force of object 2 pulling on M1 points toward M2 from the center of M1. Similarly, the gravity force of object 1 pulling on object 2 points along that line connecting the two objects. And Newton's third law still applies. Newton's third law is always true no matter what, even for field forces. So by Newton's third law, F21 equals minus F12. These two objects are exerting a gravitational force on one another. The magnitude of the force of object 2 on object 1 equals the magnitude of the force of object 1 on object 2, and those forces point in opposite directions, which is what the minus sign indicates. Now, this seems kind of weird if you're talking about two objects with really different sizes. I've already mentioned this in this class, but it's worth repeating. The gravity force of the Earth pulling down on this pen is the same as the gravity force of this pen pulling up on planet Earth. Let me sketch that situation. Here's planet Earth, and there's a little pen. That's not drawn to scale. In reality, the pen would be much smaller than that. But Earth is applying a gravity force on that pen directed downward. And similarly, the pen is applying a gravity force of equal magnitude upward on the Earth. Now, these two forces have equal magnitudes, but you notice the pen's acceleration because the pen has a very small mass. So, according to Newton's second law, that pen will have a large acceleration. According to Newton's second law, the Earth, for that same amount of force, will have a very tiny acceleration because its mass is so big.